It requires a long time to make a world like the smooth-state framework. Our insight into the universe grows remarkably each year as scientists all around the globe make sublime discoveries that change what we see today. We can talk, taking all things into account, about the most startling and less remarkable discoveries that even the most gifted experts can't sort out. Join us as we explore the depths of space and uncover secrets that help us get closer to answering the most significant questions about life. We will look at peculiar exoplanets that could disrupt the traces of physical-mechanical expertise, and rare, boundless events that nobody has had the chance to grasp. Imagine that a planet became situated inside the outskirts of our nearby planetary system, following its star in the opposite direction compared to other planets. While this type of discovery would be fascinating, it could also challenge current understandings about how planetary systems are structured. Investigators have actually found a number of these unusual exoplanets. For instance, some circle their stars in extremely close orbits, which makes the surface incredibly hot and capable of melting metals. Others are rogue planets that wander through space without a star, making us wonder where they came from and how they survive in the harsh conditions of space. Understanding the complexities of these extraordinary celestial bodies greatly impacts technological advancements. This affects both scientific curiosity and practical challenges, such as how we might live on distant worlds in the future. Each new discovery is a crucial piece in putting together the vast puzzle of the universe. Just think about what it would mean to discover water boiling on a distant world, or to find a planet with an atmosphere like Earth's. These findings could show where conditions are ideal for life to begin, helping to plan expeditions to these faraway places. Understanding the unique features and behaviors of these planets also assists scientists in refining their models of the structure and development of the universe, offering us insights into both the past and the potential future of Earth. Imagine if we find an exoplanet whose orbit is not simple, conflicting with current theories of gravity and making us question our understanding of how things move in space. While this is of significant value to science, it would also have profound effects on space exploration. The discovery of 2007 or 10, the largest known dwarf planet in our solar system that has not been named yet, is a captivating subject for research. This distant object, located in the scattered disk near Neptune, was confirmed to have been found by analyzing images from the Spacewatch project. This discovery demonstrates how space technology is often combined with scientific expertise. 2007 or 10 is the third largest known trans-Neptunian object, with a size of about 1,535 kilometers. Despite its enormous size, it remains unnamed because its orbit has not yet been fully determined with enough accuracy to meet the formal naming standards. Its surface is strangely dark and pink, indicating the presence of complex organic compounds known as tholins. These are created when sunlight interacts with simple organic molecules like methane and ammonia. Did you know that despite its size, 2007 or 10 remains anonymous due to the fact that its orbit hasn't been fully settled? Its dark surface and slow rotation make it one of the most diffuse objects in the solar system. The study of 2007 or 10 involves both direct observations and computer models that attempt to determine its orbit and characteristics. Astronomers use telescopes on the ground and in space, such as the Hubble Space Telescope. The light curves from these observations help us examine its rotation period, which takes about 45 hours to complete. This makes it one of the slowest rotating objects in the Kuiper Belt. While we once had a solid understanding of our solar system, discoveries like 2007 or 10 challenge our perspectives. Who knows what we'll find next about distant celestial bodies? These revelations not only open up more possibilities for the study of celestial objects but also suggest how we're still discovering new things in the outer solar system. Every piece of data we gather helps us dive deeper into these faraway worlds and the universe as a whole. In addition, warm Neptunes are an intriguing group of exoplanets that do not behave like typical planets. These objects orbit their stars much closer than Mercury orbits the Sun. This means their surfaces can get extremely hot, reaching temperatures over 1,700 degrees Celsius (3,092 degrees Fahrenheit). Being so close to their host stars challenges what we previously thought about planet formation and their survival conditions. These planets are so hot that they experience atmospheric blow-off, where their weather is stripped away by the radiation and winds of the star. Take K2-9b, a notably warm Neptune, as an example. Its surface temperature is so high that water molecules can't form, and hydrogen atoms break down into atomic hydrogen. Studying these planets not only challenges what we know about planetary conditions but also raises major questions about the formation and stability of planetary atmospheres. Structures anywhere on the off chance that you contrast superwarm Neptunes with explicit sorts of planets, what do you think the reasons are their shortage? Might it have something to do with how they were outlined and the conditions that should be met to make such awful settings? Permit us to understand your thought process in the comments. Is it safe to say that you are enthusiastic about the insider insights of 2007 or 2010? Really, protect until you find out about IS 1348-34. What specialists found around this exceptionally huge celebrity may be the key to figuring out how such great Goliath structures change from examining unusually warm Neptunes to examining a 1348-34. This suggests that we can continue to research the greatest, most interesting, and over-the-top matters respected to humanity. Each point develops the next one, zeroing in on the new discoveries and awe that continue to rise in innovation and make us question what we expect we perceive. IS 1348-34 is an incredibly extraordinary star in the incredibly significant bits of the superb frame of Centaurus. Other examinations of this star have figured out new insights into how perplexed the star association is. This extraordinary, limitless body, which is more than multiple times the mass of our Sun, has raised the possibility that huge stars are generally made when greater, more modest stars crash into and join with each other. All things considered, the positioning of a large circle of fuel and buildup revolving around IS 1348-34 suggests that even the best stars should form further than more humble stars do by relaxed gathering, counted from a protoplanetary disk. Such a situation makes the final results have fundamental effects. It's not just a size component. The disk around IS 1348-34 is moving and stacked with complex natural molecules and build-up particles that connect with each other positively, even in those severe conditions. This collaboration should make planet formation, which could suggest that analysts can search for new universes and possibly life in extra places. Stargazers can work on their models of ways stars expand and change over the extended period by plunging more deeply into the circle surrounding IS 1348-34. Its strong quality and the gravitational pull of its mass make it a unique spot to focus on how structure works in some of the universe's most excited regions. This observation is crucial for both outlining the life cycle of stars and exploring the potential for planets forming in places that were previously believed to be too hostile. Our next topic is nonconformist planets, which integrates the fascinating states of enormous stars like IS 1348-34 and the mysterious planets that wander the universe. These perplexing bodies, which float in space without a star to orbit, make us consider what a planet is and where they can live. Dissident planets are both conventional and scholastic. They are, in every sense, outcasts. As we continue searching for information about the field, consider what might occur to a planet that isn't held by the gravity of a star. We will find out with our next challenge, which is dissident universes. We stream from discussing huge star systems like IS 1348-34 to discussing wandering planets. This is really one of the most astonishing variables about space science. These are celestial objects that move through space without being pulled by any megastar. They're also called free-floating planets. This is completely different from the usual idea of planets as objects that orbit stars in a regular planetary system. These wandering space travelers are not held down by the gravity of any star, so they venture through the sky on their own. They challenge the popular ideas about how planets form, which say that the gravitational pull of a star is supposed to gather and form planetary bodies. Dissident planets are thought to arise in one of two ways: either they're thrown out of their home planetary systems by gravitational pulls, or they form on their own in a cloud of stars that are still developing but never end up associating with a star. Dissident planets are particularly subtle, and methods like microlensing are often used to track them down from Earth. This occurs when the distant planet briefly flashes brighter than a star as it passes in front of it. These phenomena are fascinating and provide valuable opportunities to learn more about the variables of these wandering planets. Planets that float aimlessly hugely influence how we could interpret space. They show that planetary formation is likely more dynamic and varied than we thought, and the right events for planet formation can happen in more situations than just those in which planets circle stars. The sheer number of these planets is likely greater than the stars in our own galaxy, challenging our ideas about how widespread and common celestial bodies are in the universe. It's possible that these rogue worlds are more common than stars, which raises intriguing questions about the possibility of life in these hostile environments. Could life ever exist beneath a thick layer of ice that is heated by geothermal depth on a planet wandering through space? These potential scenarios make us reconsider some new possibilities and push us to develop better methods of recognizing things as we continue to explore space. Focusing on distant planets not only helps us understand how planets form and how they survive, but also opens up new avenues for our search for life beyond Earth. Now, let's turn our attention to a fascinating area of research that looks directly into how life could begin. Complex organic molecules were found in the protoplanetary disks around younger stars. These molecules, often referred to as the building blocks of life, are formed from various carbon-based materials that are crucial for life on Earth. Protoplanetary disks are thick regions of gas and debris that form around newly formed stars. They are where planetary systems start, and complex organic molecules have been found in these environments, which are constantly developing. Subatomic building blocks, like amino acids and simple sugars, are created through chemical reactions enhanced by the energy of a young star and other processes within the disk. The discovery of these molecules in protoplanetary disks is significant because it suggests that the building blocks of life could be spread throughout the universe in these regions that eventually collapse to form new planets. This means that the fundamental conditions for life to begin could be happening all the time while stars and planets are being formed. You could think of a protoplanetary disk as a cosmic kitchen, where various materials are combined together to make a recipe. The gases, dust, and organic molecules are mixed under the influence of intense energy, much like how a baker combines flour, sugar, and eggs to make a cake. This could lead to the development of planets that could support life. This recipe sets the stage for the possibility that, when life begins to form on a planet, its essential building blocks were likely already in motion within the presence of its parent star. This discovery not only helps us learn where life could start, but it also opens up the possibility of new regions to search for life in a broader range of planetary environments. We no longer need to just look for planets with life on them, we can also consider how life might begin among the stars. The study of complex organic molecules and protoplanetary disks provides better methods for searching for life beyond Earth and raises intriguing questions about whether the building blocks of life are the same across the universe. The more we learn about the conditions that could allow life to start, the more we can broaden our search for it. As we continue to study these enormous systems, our next challenge is Kepler-78b, a planet that seems to defy conventional ideas about planet formation. This extrasolar planet questions our understanding of planetary science, yet it also captivates us with features similar to Earth. In just 8.5 hours, Kepler-78b completes an orbit around its star, which is much closer than Mercury is to our Sun.